So what can we do about multicollinearity? Well, we have a couple of issues, right? Remember, multicollinearity is when there's a relationship, typically a very strong relationship among our predictor variables. And if that happens, that can really make the whole model very hard to interpret. Another effect that it has is it increases the standard errors. We use the standard errors in order to estimate the local fit and the local parameters. We need that. We do t-tests around each of our regression coefficients to determine how far each one is from zero. And if you remember from t-tests, the denominator of the t statistic is the standard error of that particular variable. Well, if our standard errors are increased, it gets harder to detect whether or not something's going on. So increased standard errors are a problem with multicollinearity, in addition to the problem with the interpretation among all the different correlation or the regression coefficients. So we have some options. The first thing that we can do is we can increase the sample size. So if we're having problems with standard errors, and that's really the only thing that we're worried about, and we just want to increase the power, increase in power, we increase the sample size. So that's one approach that we could take. Another thing we could do is we could combine our predictors into one overarching measure, right? And we do this all the time. If we do a survey and we ask 3, 4, 5 questions in a survey that all seem to correlate with each other, that all go together, we'll combine them into a single predictor, right? And we often, in fact, we almost always do this, where we'll ask a question 4 or 5 different ways in order to get at a single construct. And when we do that, when we combine them in together, that's all we're doing. We're getting rid of that multicollinearity problem that's doing that. Because if we included each question independently in our regression equation, then we'd have multicollinearity all over the place. So instead, we combine them into one. Now, there is risk there, because when we combine them into one, we introduce measurement error. And that can be a problem. So we have to balance that risk. But combining two or more predictors together is not necessarily a bad thing to do. Our third option is we could just drop one of the predictors. Typically, we take the predictor that has less predictive value, right? Less of a semi-partial correlation coefficient, and we would just drop it from the whole thing. Now, again, this comes with risk. It certainly gets rid of the multicollinearity problem. On the other hand, there's the risk of now we have an underspecified model. We're not including everything that we could. So we have to balance that risk and make a determination. Another option is just to ignore the whole problem. Now, it turns out that our overall prediction of y will be the same. The only real problem we have here, in addition to the standard errors issue, is our interpretation of those correlation coefficients with each other. Those regression coefficients with each other. Overall, we still have a valid and maybe very high prediction of y. So if all we're interested in is the global model, the whole model as a prediction, well then getting rid of multicollinearity may not be that big of an issue. Now, if we're interested in comparing how individual regression coefficients compare to each other, so we understand which predictors are important and which ones are not, then we have an issue. Then we want to make sure that we consider the multicollinearity. But if all we're interested in is the overall prediction of the model, then maybe we make the decision to ignore it. The last option here is to center all the variables. And here we just basically calculate difference scores for each of our variables. We subtract from each individual case, we subtract out the mean for that variable. And so all we're left with is the differences from the mean for each case of our variables. This is called centering. We'll do that some more later. Honestly, it's a little controversial. Some people say you shouldn't do it. Some people say it doesn't make a difference. What can be a problem is it can change our interpretation of our results, but it is an option, and many people do it as a matter of course, as a way to get rid of multicollinearity. So I need to include it here as one of the options. Here's the bottom line. When you have multicollinearity, statistically, it just exists. As researchers and as analysts, we have to make decisions. What's important to us about this model? How is multicollinearity threatening what's important to us about this model? And which of these options for dealing with multicollinearity is most appropriate to deal with that threat? That's a qualitative decision that's going to be made by the researcher. We need to make sure that we document it. This is what we did to deal with multicollinearity. We want to show where the multicollinearity comes in and explain what we did so that anyone who wants to come replicate, anyone who's interested in our outcomes, can take a look at what our decisions were as we go. But ultimately, this is a judgment of the researcher.